a thorough introduction. Yes, indeed, I do have to explain the acronyms, especially because I realized too late that there was a typo. It's not PHC, it's HPC CFD. So I think that's a word that probably people are more acquainted with. So the question is, of course, trying to exploit machine learning in the context of CFD, but because the sort of CFD we do has some specifics around high performance computing for very large applications, this can also in itself be a challenge to use machine learning in this context.
Corentin?
Yes.
Hi, I'm Camilo. How are you?
Hi.
I think you are having you're displaying the presenter's view, not the actual presentation.
Ah, okay. Sorry, I didn't understand the answer to my. All right.
And I also have a request, Corentin.
Yes.
We are recording this presentation, and we will be recording all presentations.
Yes.
So we can also watch afterwards what you'll be presenting.
Yes.
So please keep the pace of your speaking slow.
Okay.
So it's easier to follow.
Okay. Well, it's good that you tell me that because I'm a fast talker. So I will try to keep that in mind.
Okay.
All right. Because I'm a colleague of Michael Boerem, who's talking afterwards, and we're going to be splitting our approaches to this topic, so we coordinated so as not to say the same things twice. And I'm going to start by delving a little bit into how and why the physicists should be interested in machine learning, at least, of course, give some elements, since this is a topic that is freely evolving right now. Now, the origin, this is just an overview of the French press from a year ago. Of course, everybody was talking about AI before COVID, and with a lot of positioning in the press, but the fact is that there has been a very, very big hype around AI, and of course, one of the things we want to do is to try to separate the hype from the things that are actually useful for us.
I'm sorry to interrupt, but I don't see your presentation. I just see a black screen. I don't know if I'm the only one, but.
No, I mean, you're right. You have to present to put the actual presentation, because now we have to see just all the slides and a very tiny slide. Maybe just put the other screen. I don't know.
I think you are using keynotes, so you have to go to the full screen mode.
Yeah, that's what I was doing. Okay. Maybe I can.
That's much better.
Yeah, now we see your presenting slide almost fitting the screen.
Yeah, but I'm not in presentation mode, so
it's not presentation.
I'm going to get a single screen, so things might be simpler. Hello. Yes. Okay, how is that?
Well, we are seeing on the left-hand side the slides order, and on the right-hand side the controls. So I think it's not as it should be. So maybe in the view, do you see the view panel? Maybe you can speak work with the play menu, so that you find something, so that you go to full screen.
This is what I've just done, so apparently it doesn't work. So now I'm going to disconnect my second screen so that I just have one screen. Now, I'm afraid that Teams might be a bit confused right now, so I'm going to try to start again. Do you see my keynote in non-presenter mode?
Now we are seeing this is this template window, which opens when you no, okay. No, we are seeing the slides order again.
Okay. So now if I put it in presentation with a single screen. What do you see now?
No change. I still see the sorter and the...
Maybe just stop sharing your screen and then share again. That might be an issue.
Yeah, you're right.
I think that might be a good solution.
Okay. I did do several screen changes, so it might have gotten lost. Okay. Do we have presenter mode now?
No.
Nope.
All right.
Have you select the window by starting screen sharing? You should select the whole screen and not just one application which you want to share.
Yeah.
Okay, that's a good idea. Yes. No. Microsoft Teams full screen. There we go.
That's it.
Right, that's it.
Okay, thank you. Right, so I'm gonna go a bit faster. I don't know if you've, but try to still speak at a reasonable pace. So I don't know if you've ever seen these sorts of hype curves. Some agencies try to look at emerging technologies and put them on this hype curve every year. And so, well, basically you go through a peak of inflated expectations and then a trough of disillusionment, and then finally you get back to the position where you're actually at a plateau of productivity. What's interesting is AI is all over the place here, so it is definitely established that we're in a hype cycle for AI. I thought I heard a voice. Do you still see the presentation?
Yeah, it's good.
Okay, perfect. So in 2018, deep learning was actually right there. It was at the absolute peak of inflated expectations. And in this context, we started looking at this issue. But of course, when you look at AI, the first thing you see is a lot of applications related to the GAFAM people and other companies, and not much related to the kinds of applications that we tend to look at here in physical modeling. So the question we ask is how is data science really relevant to the physical sciences? And to answer this question, well, one of the important things is to actually build a bridge between the vocabulary and the tools of machine learning and that of physics. Of course, there is a lot of applied math in common, but it does take some effort to reconcile and reconciliate the two communities. Now, to understand why it can be surprising for a physicist to look at these techniques, we have to talk about machine learning and what learning actually means in the context of a machine. Because, well, well, the first thing, of course, is that data science in general has lots of things, including machine learning. Data science is actually, when you look at the definition of statistics, it's sort of the definition of what statistics are. They're the science of data. So it's basically a new word for statistics. And in there are actually a lot of things to going on. There's data mining and big data. And then there's also a lot of statistical analysis of this data, most of which has been around for decades, if not more than 100 years. But in that field, there is a subfield, which is called machine learning, in which there is another subfield, which is called deep learning. And today, when people refer to AI, they actually usually refer to these orange and red boxes here on the bottom right, which are just parts of statistical analysis. So learning in itself is actually not that an easy concept to define. There are a lot of ways to learn. You can learn things by heart, which you did in your early years probably, but computers do that a lot better than you do if it's just about recording data. There is another, of course, concept of learning, which is more what we have in mind, which is the learning of abstract concepts and how to manipulate them and apply them. But learning could also be learning motor skills, which is also very important and is also pretty hard. You might have seen several examples. This is Boston Dynamics, which is very advanced in the field of robotics. But I mean, sometimes just putting down a box on a shelf can be a very big hassle, and the full robot actually ends up falling down. So learning is this complex word which has a lot of things actually beneath it. But machine learning in itself is actually, we can resume it by saying that it's based on Bayesian inference, which is what cognitive scientists say we actually do ourselves as humans. So basically, you could look at it by saying that you're thinking about a hypothesis, and you will have a prior here in blue on the right about this hypothesis. Maybe you believe that it's very probable or only slightly probable, and then you're presented with evidence, E. And so you're going to compute the likelihood of this evidence given this hypothesis. Let's say that my hypothesis were true, then would this data be likely? And the advantage of the Bayesian of Bayes' theorem is that it enables you to compute the posterior, so the new probability of this hypothesis given the data. You can switch from the probability of the data given the hypothesis to the opposite, thanks to this theorem. So in general, machine learning relies on this to say, I start with a certain prior. Let's say I suppose there's a linear relation between these two things. I compute the likelihood of the data given this prior, and thanks to this theorem, I can go back to a new likelihood for my, a new plausibility for my hypothesis. So another way of saying it is that your prior beliefs, H, are updated thanks to according to the evidence, by comparing it to the evidence. So in practice, what does this look like? Well, let's say that I have some data here, and you'll see machine learning is often called glorified curve fitting for a good reason. So I look at this data and I say, I'm going to have the prior belief that there is a linear relationship between the x and y axis in this data. So then I can compute the probability. Let's say there were a linear relationship, then would this data be probable? And in this case, yes, it is. There's a little bit of variance, but I think it's a very good description. So now, thanks to the Bayes rule, I can update my confidence saying, yes, this is a great model, a great hypothesis that there's a linear relationship. The problem is that this model is the learning algorithm that I chose. I said, I'm going to determine a linear relationship, and I'm going to do mean squared regression to figure out the coefficients of this this system. This is your learning algorithm. If you use that everywhere because it worked somewhere, there's no reason for it to work every time. If I look at another data set and I have the same hypothesis, maybe I'm going to say no. Given this hypothesis, the data is really not probable. So I'm going to decrease actually the strength that I consider the hypothesis H to have. This is actually a known problem. One of the first things you encounter in data science, in machine learning, sorry, it's that it's called the no free lunch theorem, which basically states that there is no great hypothesis. So there is no great learning algorithm. You can't say, oh, I'm going to use a neural network, a really deep one, because it's a very smart algorithm that's going to be good at a lot of things or at everything. That just doesn't make sense. In fact, what you're doing is trying to select the best hypothesis depending on the data that you're looking at. So if your hypothesis is very good for one data set, it will in fact make it worse for other data sets, which is why on average there is no a priori distinction between all learning algorithms. Okay, so that's all right. I can just use another hypothesis, say maybe I'll use a little bit more complex, say there's a quadratic relationship in this data. And now I can indeed find that this hypothesis is supported by the data. But sometimes the data looks like this in machine learning. And now this is an annoying case because I can go around looking for a hypothesis to try to fit this, and I never quite get something where the probability of the data is high given the hypothesis. And that is another big problem in data science, which is why data scientists spend their time looking for data all over the place. It's because sometimes the definition of the problem, so the amount of data you've collected, is ill-posed, and there is a fundamental ambiguity. You're supposed to answer two very different values for of y for the same value of x. And in this case, the only way you can get out of this usually is adding dimensions to your data, collecting more data basically for the same data points, and trying to see if there are other variables to differentiate these two. All right, so why is this tough for physicists, this way of thinking? Well, the way you usually do most science is you say, I have a bunch of inputs, and maybe I have some hypotheses about these inputs, about what's going to happen. So I have a model, my hypotheses go in. And then I use my computer, so that would be my equations, for example, and I'm going to use my computer to compute the deductions from these equations. If these equations were true, then my input would behave like this and that. And then at the end, I get a result, and I can compare this to the actual observations in the world. And if they're right, that validates my hypotheses. But in the inductive approach, which we use in learning, we do something very strange, is we flip the input and the output. In this case, what goes into the deep learning computer is the input and the data. not the model. The model is actually what comes out, because what we got at the end of what I showed you right before is we got a strengthened hypothesis because we chose the right hypothesis, basically. So what this computer is going to do in this case is figure out which is the best hypothesis that leads to the highest fit with the data. And so this way of completely changing the way we actually think about looking at data and extracting hypotheses from it is really hard to come around to when you come from a physics background. Okay, so the other thing is, of course, when you look at AI, you see a lot of very shiny superhuman algorithms that make headlines, such as AlphaGo for DeepMind. But those are actually just the tip of the iceberg. Most of the data science and the machine learning and deep learning done today in the world is actually used in the same way that regular scripts of scripting programs are used. It's just to automate very boring and very repetitive tasks. So Facebook, for example, 300 million images are deposited every day on Facebook, and each of them is seen by at least 7 different neural networks to check for ads or maybe things that you need to censor or things like that. And there are more than 100 billion words per day translated on Google Translate. So most of what's actually happening, most of the compute power used in deep learning is to do things that are really not at all superhuman. They are just hard to automate by hand. We don't really know how to make a translator that works other than with a learning algorithm, but that doesn't make it extraordinarily smart. So one way to think about this is you can very broadly define intelligence by the amount of skill you can achieve given a certain experience. So if, of course, you live in the top left of this chart, it means that with very little experience, you can achieve very high level of skill. And so this could be considered as being highly intelligent. Whereas if you need to try over and over and over again to reach only a mediocre level of skill, then maybe that's not very smart. And humans in this graph, compared to all learning systems that we know, artificial and natural, are actually pretty high up in the top left here of this graph. Some babies on some examples are able to generalize from a single instance and a single example. So they have one experience and they deduct the actual law behind it. So humans are, for reasons that we don't understand fully today, very, very good in this graph. And machine learning, let's say it right now, even at DeepMind, the best algorithms they have today are much, much less intelligent in the sense that the slope in this graph is much lower. They need much more experience to achieve the same level of skill. But they do have one way of cheating, is they can earn several equivalent lifetimes of a human of experience in a couple of hours. So the software AlphaZero, which is the #1 software in the world at playing Go today, if it only plays 100 games, it cannot play Go yet, whereas a human would have really started to understand the rules of the game. But AlphaZero is trained by playing 21 million games of Go in 24 hours, so much, much more than a human would be able to play in his lifetime. And this is how, in fact, these algorithms, which have lower intelligence, through raw power, if they can gain enough experience, can sometimes achieve superhuman performance, skill. But again, let's not forget that this is the shiny emerged part of the iceberg. Most of what's happening is happening in the bottom left of this graph. Okay, so how, as a physicist, should I look for a good machine learning problem? Well, if you look at the Google Machine Learning Crash Course, they actually give some rules about this. The first thing is you should focus on problems that would be difficult to solve with traditional programming. Otherwise, oftentimes you end up spending a lot of time finding data and figuring out approximations for things that you already know how to solve efficiently with traditional programs. Neural networks are actually often called intuition machines. So if you know how to do something, but you don't really know how you do it, that's a good indicator, because that means that task is possible. Somehow the human brain does it, but we don't know how to write a script to do it because we don't know how we do it. For example, if I show you this picture of a cat and I say, where's the cat? In the sense, what are the pixels associated to the cat? You do that instantaneously. You know that this yellow area here is the cat. But for some reason, you don't really know how you did that. You don't know how you decided that the background up there is not the cat, but you don't even really know how you decided that the reflection that you see of the paws under the cat are not the cat either. You actually have several complex models, visual models, and also models about the physical world that come into play automatically to figure out what pixels are or aren't the cat, but you don't know where they came from and how they work. So if you have to write this script in C or in Python or whatever, you have no clue where to start to actually do this. So this is, of course, the kind of thing that neural networks do and do very well. Other things that are important is knowing the problem before focusing on the data. Even data scientists know this, so it's not just giving a hard drive full of data to someone and say, figure something out with your automatic smart thing. It's really very important to understand finally what the problem is and how the data will interact with it to be able to solve it, even with automatic learning algorithms. You need a lot of data, and we'll come back to what a lot of data is in a second. And also, you shouldn't let the machine learning do the hard work of choosing the features for you. So there's actually a lot of intuition guiding in teaching training and using training algorithms. It's not about dumping a million variables and then letting it figure it out. That actually oftentimes doesn't work at all. The learning problems that yield very good machine learning solutions are problems that have been very well refined to contain just the right amount of data and just the right amount of information and signal to noise ratio, in a sense, in the input. Okay, so what's a lot of data? Well, as physicists, that's an important question. I want to get in machine learning. How much data should I take? Well, as we said earlier, these algorithms are not very smart. So if you give them low experience, they will just yield low skill. So it really depends on the level of skill that you're trying to achieve. But the fact is that if you take scikit-learn, which is maybe the most popular, one of the most popular machine learning frameworks today in the world, it gives you this flowchart of figuring out which algorithm you're supposed to use for each case. So you start here, and then the first question they ask is, maybe you don't see it, is do you have more than 50 samples? And if the answer is no, it says, well, machine learning can't help you. And so this is important because there are a lot of people who try sometimes to apply these tools, and they will work and give you results on extremely small data sets, but it's really not recommended because that's forgetting how dumb they are, in a sense, and how little they're able to extract information from so little data. So in a sense, you could sort of draft an axis like this, saying that below 30 samples, it doesn't make much sense to talk about statistical analysis. Or at around 10 to 30 samples, you can start using some very simple statistical tests or very simple regressions. And then when you get to the hundreds and thousands, you can start using more machine learning techniques like regressions and support vector machines and so on. And the neural network territory is really when you go to the much higher and larger data sets afterwards. What happens when you don't have enough data? I like this example, although it's a bit tragic, but if you've ever heard of the earthquake frequency estimation law, there's the Gutenberg-Richter law, which is basically just a linear fit in this log graph of frequency versus magnitude. And it's been verified many times all over the world. And this up here is the Tohoku area in Japan, where Fukushima was constructed. And this is the dots that were used and the regression that was used when they actually measured the frequency of earthquakes in that area and designed the Fukushima power plant. So what they did here is they did a polynomial regression saying, oh, it's interesting. We don't really have this linear fit. We have another, we have something that's happening here around magnitude 7.3. And so this would be a better fit to the data in this case. And then they said, let's design the power plant so that it can sustain the 1 every 1,000 year earthquake. And that gave them an 8.6 magnitude. The problem is that that's underestimating several things about data. The first is that this is a log graph. So the top line here is once every 10 years. And this data was actually recorded over the course of about 35 years. So maybe they saw something like 3 of the magnitude of 1 in every 10 years. And then they have some points there close to the 1 in every 100 years line. And so one wonders how they actually came up with those points by only observing for 30 years. But the fact of the matter is that these points that you have on the right and that motivated the polynomial regression are actually supported by very, very little data. And so this is really an overconfidence fit of very, very low amounts of data. If you actually do follow the Gutenberg-Richter law, as you should, you obtain, in this case, a curve that looks like this. And in fact, you realize that the 9 to 9.1 magnitude earthquake that did lead to the Fukushima disaster has a probability of occurring of 1 in every 300 years instead of 1 in every several thousand years, as was previously estimated. Okay, I think I've said enough about machine learning in general. I hope I'm going to show you two really more concrete case studies so that you can have an idea of what we can do today with this sort of approach in CFD. Now, if you actually want to use AI in CFD, once you've said that, and that's your goal, there's actually a lot of ways to do it, and it's not very clear today what the best way is. It depends on your objective, of course. Because when you're doing CFD, roughly you can say that you start from some inputs. Oftentimes you're going to discretize it. At least a lot of people listening today, that's how they start. And then you're going to estimate spatial and temporal gradients and insert your models, do everything you need to do to time step, and so reach the next time step. And you can either repeat that process for a while until you've reached the end time that you've given yourself, or when you're happy, you can say, okay, I'm done, and these are my results. So when I look at this graph, where should I insert AI in this thing? Where should I insert a deep learning approach? Well, you can do it in many ways. You can do a surrogate, and a lot of people have been doing this way before we were calling it machine learning, where you just try to skip this whole process altogether. You can also act on the meshing operations through optimization or automatic meshing and things like that. You can act on the gradient estimation, on the models themselves, for example, making them more accurate, or on the time step. You can try to use larger time steps thanks to approximations and learning so that your computation will go faster. And so there are many ways that AI, you can introduce or intrude with AI into the CFD standard process. So today it's not clear what way to go, and I'm going to show you two examples that we've tried to go into. So the use case one will be on more accurate models. Use case two will be on the better gradient estimation. So the first one is subgrid scale modeling with convolutional neural networks. Now, the target that we have here is combustion, and the idea is that we're trying to take some simulations that we're reasonably happy with today when they are on the order of maybe 10 centimeters, and move all the way up to simulating explosions in buildings for safety issues, and when you have a gas leak, for example. And the problem is that the domain is very large, but the flame is still highly turbulent, and so you have very thin, very wrinkled flame in a very, very large environment. And so in this case, you're trying to do reactive LES of very large domains, and this is of course very tough on the subgrid scale models in this case. So a subgrid scale model, well, very simply speaking, you could say it's just that I have a certain grid here, my LES grid in green, and so I can represent certain physics on the bottom, but that's just what I can pay for in a real configuration. Whereas I actually know that if I were to resolve the full physics to do a DNS, I would need a much finer mesh. So the topic of subgrid scale estimation here is, modeling here is basically to estimate what's missing between these two situations. So what's actually nice with this is that if I run a simulation on the fine grid, and then I filter it to represent an equivalent LES on this grid, an equivalent low-dimensional representation, because I started with the blue mesh, so all the information, I can also estimate what was lost during this filtering, and this actually sets up a training problem. I have an input, which would be my normal under-resolved simulation, and the output, which is what the model should have said on these examples. And in this case, what I want to do afterwards, of course, once I've trained a network to do this, is to actually put it in my physical solver and use it as a model for my solver. So we did this on flames because when you look at a resolved flame, it really looks like what I showed you before. If you have a resolved grid like this, you can see a lot of wrinkles in the flame. But once you have a coarser mesh, this is a very geometric problem, actually, which is you're just losing surface because you can't represent it on your coarser mesh. So a lot of work has been done on this, of course, and there are a lot of local formulations that have been suggested to try to estimate this amount of wrinkling that is missing in the coarse mesh compared to the fine one. But in recent years, several works have shown that actually integrating more than just local information, integrating two different zooms, if you want, one local and one a little bit more zoomed out of information, actually increases the quality of the subgrid scale model in this case. And so this is why we went to a convolutional neural network, which is actually, the natural extension of this, because a convolutional neural network basically learns the impact of a number of scales from very small to very large around an area to make the best estimation possible. So we built the data set by filtering, as I said, and then only working with the CNN in the LES mesh. This is an important point. A lot of people start with learning on try to think about running DNSs and then learning on DNSs. But one of the issues with that is that you end up with an end product, a neural network that only knows the DNS world and might get completely lost if you show it LES data. So here we had a setup where we actually only use the neural network in a context where it's seen LES meshes, because this is where we want to use it later on. The neural network itself was taken from the literature, taken from image segmentation in medical image segmentation, actually, so medical field, slightly adapted, but it's a really pretty straightforward neural network in this case. We did look at a little bit of interpretability for this network, because actually when you look at these layers, so I won't detail what's happening here, but basically the information flows from the left through all these arrows all the way to the right of the network. And as it does, we know that something called the receptive field, which is how far the information is integrated into the decision from the network to decide what the value should be at one point, we can actually track this as we go down through the network. And so we know that this network looks at roughly 30 points around every one to make its determination. And so this is how we design our data set, our database, our simulations, etc. Okay, so the a priori strategy we use to estimate this is to say you have your training set up. So I described that you run a simulation and then you train your neural network to try from the filtered fields to produce the subgrid scale model. And then you run another separate simulation with a DNS that you do with a DNS solver. And then you filter that. So it's a separate simulation, but because you filtered it, this is what the CNN expects as an input. So you can, in this case, you know the truth, of course. So this is really an a priori, standard a priori strategy. You know the truth, but you can also give the filtered field to the neural network, and it can try to predict the amount of missing flame wrinkling, so the target subgrid scale value. And you can make a detailed comparison of the two in this case. So the DNS for training was a standard turbulent burner, and we tested it on a case that was rather different from the training case, where we changed the input speed for a little while and then took it back. So we had this big different structure, this big mushroom, because we wanted to check that the network actually worked on something else than the exact case that it was trained on. And in this case, we were pretty happy with the results. So you have here at every X position the amount of flame surface. And so the LES is in purple, it's at the bottom. And then the DNS, the actual flame surface at each position is the blue dots. And so the CNN model here, the neural network, was very close to the DNS in this case, even though this is not the case that it was trained on. So that was a good agreement compared to the literature. But then we also need, if this works, we also need to put it back into an actual solver, because if it's not that easy and that trivial to put a neural network inside a solver. So the strategy here is a little bit different. We start from the same training as before, so we validated that training already in the a priori setup, and now we use another target setup, but now we have to modify a code. And so this is a special version of AVBP here, AVBP-DL, which is used to perform the LES, in fact, of this setup, but to perform it with the convolutional neural network inside. So at each iteration, when you actually have to fill in that subgrid scale model value, you interrogate the neural network and it gives you the value for the full field, and then you can move on to the next iteration. And the result is you can compare the filtered DNS and the AVBP-DL LES. The problem to do that is you need to have a modified version of your code, and so we did modify AVBP in this case. But one of the issues with neural networks is they're pretty expensive to run at inference, but they're very fast on GPUs. So we went to hybrid architectures in this case to be able to solve for AVBP on the CPU, but to do the inference of the network, so to run the neural network basically on the GPUs, which meant that we had to couple all this, and there was quite a bit of HPC involved in this process. The result was relatively satisfying at first try here. So in this case, sorry, we had a better agreement with the DNS thanks to the CNN model in a posteriori than we did with models from the literature. But this was rather preliminary work. There has been more on this in recent times. But one of the big challenges to have more is to be able to scale this. So we've mostly focused on the HPC side of this recently. And we did a challenge last summer and continued this year on scaling this up to several thousand CPUs and several dozen GPUs. So we have 2 domain decompositions, one for the Navier-Stokes solver, one for the neural network. And so this is all ongoing work in a PhD at Surfax, but it's starting to work pretty well. And so I think we'll have soon the tools to investigate this further on very much larger simulations. All right, so this was use case 1. I'm not sure where I am on time because I'm not sure where we defined the starting point. But
12 minutes.
Okay, all right, that's fine. So there is another, maybe I did speak too fast once again, I'm sorry. So the second use case where we can try to look at optimization thanks to AI in the chain is in the gradient estimation step. So here we're based on some work that I'm going to try to explain. Take back what I was showing earlier. So you have what you can pay for and then the fully resolved physics. Sometimes you need a subgrid scale model, but other times you have some physics which you just need to represent as very fine. You don't always have a model that enables you to represent it in a much thicker way. So if you have a fine mesh like this, you can actually have reasonable amounts of points in your gradients. But if you start going to coarser and coarser meshes, you just can't represent your gradient anymore. And this poses a lot of problems for numerical schemes. So in practice, if you start on a fine mesh here, the simulation on the left, this is just a Bergquist equation simulation, but on a very fine mesh, it works fine. And then when you make the mesh coarser and coarser, it becomes harder and harder for the numerical scheme to follow. And it's not able, after a while, it just crashes. It's not able to maintain the physics. But here we're going to look at a method that actually enables to go much further in this direction and to be able to hold simulations that stay reasonably accurate and that also are stable and don't crash, even on much coarser meshes, which should open the way to actually running simulations of this kind of configuration with much less mesh points and so much faster. So how do they do this? Well, if you look at a standard resolution, you start from time t, and then you're going to compute your spatial derivatives. And the way you do this is using some preset coefficients or some coefficients that you compute from theory. And so you have this estimation of the spatial derivatives, which you can then send to compute your fluxes, and then estimate your actual time derivative, which enables the time stepping and going to t+1. The step that they get in here with the neural network too is the one on the top here. What they say is, well, how did you compute these spatial derivatives? We have some analytic ways of suggesting how to compute them, but in fact there is some freedom in there. As you can have a certain polynomial accuracy of your numerical scheme, sorry, but that doesn't mean that you know exactly how to choose that numerical scheme given a numerical accuracy. And there's some leeway in there, and we're actually not always sure how to do it. And a lot of people will change the way they do it dynamically depending on what the flow is showing. So what they're doing here is saying, let's let the network choose under a certain polynomial accuracy constraint which exact way it wants to estimate the spatial derivatives. So this is one of the less intrusive approaches because you're using 90% of an actual CFD solver. In this case, you're even guaranteeing the polynomial accuracy of your numerical scheme. But the objective, of course, is to get better gradient estimation on coarse meshes, and so to be able to run coarser simulations and get the same result. And we've translated this to, so this was not Berger's equation, but we've been doing this in PhD on Euler's equation. So here you have, in the center, you have the true DNS, so the DNS of the problem, which has been filtered on a coarse mesh to compare. And then on the right, you have the actual coarse LES with the same numerical scheme, which is able to solve it in this case, but it's killing a lot of the gradients. And then on the left, you have the technique with the neural network, which is suggesting the way to compute the spatial derivatives. And so I hope you see this movie, and you can see that the DNS in the center and the coarse LES with the neural network on the left actually have a lot of common features. Now, of course, after a while, this is not the same turbulent realization, so there are some minor deviations. But in practice, you can see on the right that even a very good numerical scheme in this case is not at all able to represent the gradients that you have. Okay, so this is a great idea, but it has quite a difficult execution. One of the first challenges, of course, is that to train a neural network, you need to do something called backpropagation of your errors. So you need to be able to take any error that it's making at the output and to go all the way through your solver, so whatever operations you're doing, and they must all be differentiable. So in practice, that means you need to rewrite a CFD solver in a deep learning framework usually. But there are now several teams that have been working on this, and there are even some first software initiatives of CFD software fully rewritten in deep learning frameworks. So this is something that's becoming possible. The other challenge is time stability, because in a supervised manner, you're telling the network at the next iteration, you're supposed to produce this result, but in that, you're actually letting some small errors be introduced, and you can't really control how these errors evolve over much longer lengths of time. So the management of these time stability issues is a difficult one in this case. The other thing is that if you try to say, well, you have to have the next 10 iterations or next 50 iterations right, after a while you start to punish the network not for having errors or for diverging, but for actually just having a different turbulent path, because the DNS and of course the LES won't yield exactly the same turbulent path. So this is much more work in progress, I would say. Okay, I'm going to move to some concluding remarks. I want to just give you a small overview of some general areas in learning that I've discussed and others that I haven't. One of the obvious applications for neural networks is supervised learning. For any machine learning is supervised learning. That's what you'll find in most tutorials. That's the easiest to get into. Okay. So in this, we're looking at several problems, such as in predictive maintenance and in image segmentation. I didn't show you, but we also do some forest fire flame front tracking, and there's also some sound classification, interesting sound classification. But none of this has anything to do with CFD, so I can talk about it if you're interested. But I left it out. There's also regression, so that's what I showed you, replacing local physical models with convolutional neural networks, and we also do some work on time series. Now, a second important aspect for CFD is the performance side. And so we can look at performance for several isolated but interesting topics, such as data compression. But there's also the big issue of actually using physical solver approximators, not necessarily full surrogates, but some issues here will be discussed by Michael in the next presentation. And in any case, running this in an actual HPC context is a big challenge. And so that's where also hybrid solvers in the HPC context are important. And that's what we've been doing with these explosions. And finally, there's a full other aspect on generative learning. Now, this is something that's tougher to get into. There are some applications here, but not quite on CFD yet either. Generative tools, you might have seen neural networks that generate faces or things like that. They're extremely powerful tools in the sense that they really can do things that no one could imagine doing just 10 years ago in the field of computer vision. But the applications to CFD are very scarce for now, and I think we've yet to see some convincing ones. There are more in the data assimilation field, and maybe possibly in some synthetic data generation too. All right, and just the last topic is reinforcement learning that I didn't get into at all, but I think this is also something Michael will talk about in the next presentation. Okay, thank you.
Thank you very much.
Thank you, Corentin. I will stop the recording.